Suppose you've calculated the equation of a best fit line. A question that might occur to you is, how well did my line actually fit the data that I have? In order to figure that out, we use the coefficient of determination, or R squared. This indicates the percentage or the fraction of the observed variation in the y variable that is explained or accounted for by a least squares regression line. Now, to calculate this, it's not too difficult. It's tedious to do by hand, but it's not too difficult conceptually. We calculate first the total variation in the y variable about its mean. And the way we do that is we generate this total sum of squares, or SST. We take the deviation in each y value from the mean of all the y values, and then we square that deviation. Then we add up the sum of the squared deviations, and that's what the SST is. This measures the total observed variation in the y variable about its mean. So that's what we're trying to explain with the line. This is sort of like the total variation in y that we're trying to explain, and hopefully we can explain at least some portion of that with our best fit line, or at least account for some of that with the best fit line. Residual sum of squares is something you've seen before. We call this SSR. That's the sum of the squared residuals. You take a y value, you subtract the predicted y value for that same value of x, you square that residual, and then you add up all the residuals, all the squared residuals, and get this SSR. This is the part of the observed variation in the y variable that is not accounted for or explained by the least squares regression line. Now, ideally, this would be a very, very small quantity relative to that SST, and that would mean that our best fit line was doing a really good job of accounting for the variation in y that we see. The part of the observed variation in the response that is explained by the least squares regression line is just the difference between the total sum of squares and the residual sum of squares. And the fraction of the observed variation in the response that is explained by the least squares regression line is going to be that quantity divided by the total sum of squares. And that's what R squared is. The difference between the total sum of squares and the residual sum of squares divided by the total sum of squares. And this will give us a fraction of the SST that's explained by the line. It's basically the total variation minus what's unexplained. That gives us the explained portion. We divide that by the total sum of squares, and we get the fraction of this that's explained by the line. Okay, R squared is the square of the correlation. Even though it looks like we came at it from a totally different point of view, algebraically, if you were to break this down and square the correlation formula and do a lot of algebra, you could show that this is actually equivalent to the square of the correlation formula. Now, since correlation is some number between 0 and 1, negative 1 rather, and 1 inclusive, R squared has to be between 0 and 1 inclusive. And the closer R squared is to 1, the better the least squares regression line is doing at explaining the variation in the response variable. Now, we looked at an example in a previous video where we were trying to find the correlation between the price that houses are listed for when they're put up for sale and the size of those houses. And the correlation that we got was 0.8357. R squared in this case would be the square of that number, 0.6983. And that means that 69.83% of the observed variation in listing price is explained by the least squares regression of listing price on house size. So whenever you have to interpret an R squared, you're just going to follow this basic idea. Just follow this structure right here. Say what percent, that is, express R squared as a percentage, of the observed variation in, and then you put your y variable in, is explained by the least squares regression of, and then you put the y variable on the x variable. And that's all you have to do anytime you're trying to interpret this. Another way of saying this is 69.83% of the observed variation in listing price is explained by a straight line relationship between listing price and house size. So that's another way that it might be worded. But this is probably the easiest and simplest to work with. Now here's an example of how you can calculate R squared. This is starting from a very simple set of numbers and a very simple best fit line, and then I'll show you how we get the SST and the SSR and calculate the R squared. So we've got 4 points, 2, 5, 4, 4, 6, 7, 8, 6. I plotted them on this scatter plot here. The mean of the x values is 5. The mean of the y values is 5.5. The standard deviation of the x's is about 2.582. And the standard deviation of the y's is about 1.291. And the correlation between x and y is 0.6. If you use those summary statistics, you can calculate the equation of the best fit line to be y hat equals 4 plus 0.3 times x. And I've drawn that best fit line in the picture as well. And you can see this point has a positive residual, as does that one, and these 2 points have negative residuals. Okay, so the line didn't fit all the points perfectly, so it's not going to explain all of the variation in y, but let's figure out what fraction of the variation in y the line actually accounts for or captures. Okay, the first thing we're going to have to do is find these residuals, and you can do that by plugging in these x values into here and then subtracting those results, those predicted values from these, and that'll give us a y hat for this point right here, 4.6. If you plug in 2 right here, you get 4 plus 0.3 times 2, and 4 plus 0.3 times 2 is 4.6. If you plug in a 4 here, you're going to get 4 plus 0.3 times 4, which is 5.2, etc. And the other residuals, or the other predicted values, are 5.8 and 6.4. The residual for this point right here is positive, it's 0.4. For this one, it's negative, it's 1.2. For this one, positive 1.2, and for this one, a negative 0.4. You can see if you add up the residuals, they would add up to 0. The positive ones cancel out the negative ones, and that's the way it always has to be. Okay? And here we're measuring deviations from the mean. So I subtract 5 minus 5.5, I get negative 0.5. 4 minus 5.5 is negative 1.5. 7 minus 5.5 is positive 1.5. And 6 minus 5.5 is 0.5. So these are the deviations of the y values from the mean of all the y's. We square those and add them up, and we get the total sum of squares, which is 5. To find the residual sum of squares, we square all these residuals. We get 0.16, 1.44, 1.44, and 0.16, and we add them up and we get 3.2. So this is the residual sum of squares. The part of the variation in y that the line is actually accounting for or capturing is the difference between these two things. And then we divide by the total sum of squares to express that as a fraction of the total variation. Okay, so we take 5 minus 3.2 divided by 5. That's 1.8 over 5, which is 0.36. So this is 36% of the observed variation in y is explained by the least squares regression of y on x. Now, if you look at that number, you'll see, okay, there it is. It's the square of the correlation, which was 0.6, and that's the way it should be. Even though this doesn't look a whole lot like your correlation formula, it contains a lot of the same information, and this can be shown to be the square of that correlation formula with a lot of work, and that's too much work to get into here. But if you're curious, I'm sure you can find derivations of that online.